For most of human history, the universe has felt impossibly vast, silent, and unreachable. Even as our technology has advanced and our telescopes have pierced deeper into the cosmic darkness, one truth has remained stubbornly intact. Space is enormous and travel across it seems fundamentally limited. The stars appear close in the night sky, yet they are separated by distances so extreme that even light itself requires years, centuries, or millennia to cross the void. This realization has shaped our understanding of what is possible and what must remain forever beyond reach. But what if that assumption is wrong? What if the universe is not a vast open ocean with no shortcuts, but instead a hidden network of passages, tunnels, and intersections woven directly into the fabric of space-time itself? What if the greatest obstacles to cosmic travel are not distance and speed, but ignorance of the architecture that already exists beneath our equations and observations? We are familiar with black holes. They are among the most extreme objects ever predicted and observed, regions where gravity becomes so intense that not even light can escape. They represent the ultimate dead ends of the universe, places where information seems to vanish and the known laws of physics stretch to their breaking point. For decades, black holes have symbolized destruction, finality, and the absolute limit of exploration. But black holes may not be the full story. In the shadow of these cosmic giants lies a theoretical possibility so strange, so counterintuitive, that it challenges not only our understanding of space and time, but our assumptions about reality itself. A possibility first hinted at in the equations of Einstein's general relativity, then quietly explored, debated, dismissed, and resurrected by generations of physicists. These hypothetical structures are known as wormholes. Wormholes are not science fiction inventions. They are not the product of fantasy or cinematic imagination, even if popular culture has embraced them enthusiastically. They emerge naturally from the mathematics that describes gravity and space-time. In their simplest form, wormholes are shortcuts through space-time, connections between distant regions of the universe, or perhaps even between different universes altogether. Imagine folding a sheet of paper. 2 points that were far apart on the flat surface suddenly touch. A hole punched through the fold creates a tunnel between them. In this analogy, the paper is space-time. The surface distance represents conventional travel, and the hole is a wormhole, a path that bypasses the long journey entirely. If such structures exist, then the universe may be far more interconnected than it appears. The vast distances that separate galaxies might be illusions imposed by our limited perspective, concealing an underlying geometry that allows rapid or even instantaneous passage between distant points. This idea is deeply unsettling. It forces us to question the fundamental nature of distance, causality, and time. It also raises uncomfortable questions about energy, stability, and the limits of physical law. Wormholes, if they exist, are not gentle or benign. They would be born from extreme gravitational conditions, teetering on the edge between existence and collapse. To understand wormholes, we must first understand the environment from which they arise. This means confronting the nature of space-time itself. In Einstein's view, space and time are not passive stages upon which events unfold. They are dynamic, flexible, capable of bending, stretching, and warping in response to mass and energy. Gravity is not a force in the traditional sense, but a manifestation of curved space-time guiding the motion of matter and light. Black holes are the most dramatic expression of this curvature. When enough mass is compressed into a sufficiently small region, space-time collapses inward, forming an event horizon beyond which escape becomes impossible. At the center lies a singularity, a point where density becomes infinite and the known laws of physics cease to function. Yet within Einstein's equations, certain solutions suggest that space-time does not always terminate at a singularity. Instead, it may extend through it, forming a bridge to another region. These solutions, known as Einstein-Rosen bridges, were among the earliest mathematical descriptions of wormholes. Initially, they were regarded as mathematical curiosities rather than physical realities. The prevailing belief was that such structures would be violently unstable, collapsing almost instantaneously before anything could pass through. Wormholes, if they formed at all, would be fleeting, microscopic, and useless for travel. But theoretical physics has a habit of revisiting discarded ideas. As our understanding of quantum mechanics deepened, and as new insights into energy, vacuum fluctuations, and exotic matter emerged, wormholes returned to the conversation. Not as simple tunnels carved through spacetime, but as complex, fragile structures requiring conditions far beyond anything we can currently engineer. One of the most intriguing aspects of wormholes is their relationship to black holes. In some theoretical models, black holes may be the mouths of wormholes, acting as gateways rather than endpoints. From the outside, they appear indistinguishable from ordinary black holes, consuming matter and light, but beyond the event horizon, space-time could open into a tunnel rather than collapsing into a singularity. If this is true, then black holes may not be cosmic graveyards, but cosmic junctions. Guardians of hidden pathways that connect distant corners of the universe in ways we have barely begun to imagine. This possibility radically alters our understanding of cosmic structure. Instead of a universe defined solely by expansion and isolation, we may inhabit a spacetime web, where regions that appear distant are secretly adjacent through higher dimensional geometry. The implications are staggering. Interstellar travel, long considered impractical due to energy constraints and timescales, could become theoretically possible without violating the speed of light, not by moving faster than light, but by taking a shorter path. Time itself becomes part of the discussion. Wormholes do not merely connect points in space, they may also connect points in time. Under certain conditions, wormholes could allow closed time-like curves, paths that loop back into the past. This introduces paradoxes that strike at the heart of causality and logic, challenging our most basic intuitions about cause and effect. These are not fringe ideas, they are explored seriously in peer-reviewed physics, debated by leading theorists, and constrained by rigorous mathematics. Yet they remain speculative, balanced delicately between what is mathematically allowed and what is physically plausible. As we venture deeper into this topic, it becomes clear that wormholes are not simply tools for travel. They are probes into the deepest questions we can ask about reality. What is space-time made of? Is the universe fundamentally local or profoundly non-local? Are distance and separation emergent properties rather than absolute truths? The search for wormholes is also a search for evidence. Astronomers and physicists are examining gravitational waves, black hole shadows, and cosmic background radiation for subtle anomalies that might hint at hidden connections. Some suggest that the universe's apparent randomness may conceal patterns imposed by a deeper topology, one shaped by unseen tunnels and shortcuts. At this stage, wormholes remain theoretical. No confirmed observation has proven their existence. But absence of evidence is not evidence of absence, especially in a universe as vast and complex as ours. The history of science is filled with ideas that were once dismissed as impossible, only to become foundational truths. Black holes themselves were considered mathematical oddities for decades before observational evidence forced their acceptance. Gravitational waves were predicted a century before they were detected. The universe has a habit of being stranger than we expect. As we move forward, we must ask ourselves a question that is both scientific and philosophical. Are we truly confined to a universe where distance is destiny? Or are we standing at the edge of a deeper understanding, one where the cosmos is threaded together by invisible highways beyond our current reach? This is only the beginning of the journey. To understand wormholes, we must confront not only their promise, but their profound challenges. The physics that governs them is unforgiving, the energy requirements extreme, and the risks existential. In the next part, we will dive deeper into the mechanics of wormholes themselves, how they form, what keeps them open, and why the universe seems reluctant to allow their stable existence. The answers are as fascinating as they are unsettling. To move beyond speculation, we must confront the physics of wormholes head-on. These structures are not magical passages waiting to be discovered. They are extreme solutions to Einstein's equations, demanding conditions that push reality to its limits. Understanding how wormholes might form requires us to explore the most violent and energetic environments in the universe. In theory, wormholes could emerge naturally in the early universe. Moments after the Big Bang, space-time itself was chaotic, dense, and turbulent. Quantum fluctuations were amplified to cosmic scales, and gravity had not yet settled into the smooth, large-scale structure we observe today. Some models suggest that microscopic wormholes may have formed during this primordial era, fleeting bridges connecting different regions of spacetime, before collapsing or shrinking beyond detectability. These hypothetical remnants, often called quantum wormholes, would be incredibly small, far smaller than an atom. They would flicker in and out of existence within the quantum foam, a seething background of space-time fluctuations predicted by quantum gravity theories. While these wormholes would be useless for travel, their existence could have profound implications for the nature of space-time itself. But macroscopic wormholes, the kind imagined as cosmic highways, require something far more exotic. The primary challenge is stability. Gravity is relentless. Any tunnel carved through spacetime would naturally want to collapse under its own gravitational weight. To prevent this collapse, wormholes require a form of matter with negative energy density, often referred to as exotic matter. This is not antimatter, nor is it simply hypothetical fantasy. Negative energy densities are permitted by quantum theory and have been observed in small amounts through phenomena such as the Casimir effect. In the Casimir effect, two closely spaced metal plates experience an attractive force due to changes in the vacuum energy between them. This demonstrates that the vacuum of space is not empty, and that energy levels can be manipulated in counterintuitive ways. In principle, if negative energy could be concentrated and controlled on a massive scale, it might be capable of holding a wormhole open. This is where theory begins to strain against practicality. The amount of negative energy required to stabilize a traversable wormhole would be enormous, potentially comparable to the mass energy of entire stars. Even optimistic models demand technologies far beyond anything currently imaginable. The engineering challenges alone verge on the absurd, and yet physics does not forbid it outright. Another obstacle lies in tidal forces. The intense curvature of spacetime near a wormhole throat could stretch and compress matter catastrophically. Any traveler attempting to pass through would be subjected to gravitational gradients strong enough to tear atoms apart unless the wormhole were sufficiently large and gently curved. This again raises the energy requirements to staggering levels. Then there is the question of causality. Wormholes blur the line between space and time in dangerous ways. If the two mouths of a wormhole experience different gravitational fields or relative motion, time dilation effects could cause them to become temporally misaligned. In such cases, traveling through the wormhole could result in arriving at a destination before departure, effectively creating a time machine. This possibility deeply troubles physicists. Time travel introduces paradoxes that threaten the consistency of physical law. The grandfather paradox, information loops, and violations of cause and effect are not merely philosophical curiosities. They undermine the predictive power of science itself. Some physicists argue that the universe enforces a form of chronological protection, preventing macroscopic time travel through unknown mechanisms. These could include quantum instabilities that destroy wormholes before paradoxes arise, or deeper principles not yet understood. Interestingly, recent developments in theoretical physics have reframed the wormhole discussion in unexpected ways. The connection between wormholes and quantum entanglement has become a topic of intense interest. The idea, sometimes summarized as ER equals EPR, suggests that entangled particles may be connected by microscopic wormholes, not traversable tunnels, but geometric links embedded in spacetime itself. If true, this would imply that spacetime connectivity is deeply tied to quantum information. Distance in this view is not fundamental. It emerges from patterns of entanglement. The universe becomes less like a smooth continuous fabric and more like a network, stitched together by invisible threads of correlation. This perspective has profound consequences. It suggests that wormholes are not anomalies, but expressions of a deeper organizational principle. They are not rare cosmic accidents, but natural features of a universe where geometry and information are inseparable. From this angle, black holes take on new meaning. Rather than destructive voids, they may be laboratories where space-time and quantum mechanics intersect most vividly. The information paradox, long a source of confusion, may be resolved through hidden connections that preserve information via non-local pathways. Observationally, detecting wormholes presents extraordinary challenges. From the outside, a wormhole could mimic a black hole almost perfectly. It would exert gravitational influence, bend light, and distort space-time in similar ways. Only subtle differences in lensing patterns, accretion behavior, or gravitational wave signatures might betray its true nature. Some researchers propose that certain unexplained astrophysical phenomena could be consistent with wormhole effects. Unusual brightness fluctuations, anomalous lensing events, or unexpected correlations between distant regions of space could hint at hidden connections. These ideas remain speculative, but they are guiding observational strategies. Gravitational wave astronomy offers new possibilities. When massive objects collide or merge, they send ripples through spacetime. If wormholes exist, their interactions could produce gravitational wave signatures, distinct from those of black holes. Future detectors with greater sensitivity may be able to distinguish these subtle differences. As our instruments improve, the line between theoretical curiosity and empirical science grows thinner. Wormholes may remain elusive, but they are no longer confined to chalkboards and equations. They are becoming testable, at least in principle. Yet even if wormholes exist, the question remains whether they can ever be used. Nature may permit their formation, but forbid their exploitation. The universe may allow shortcuts without allowing travelers. This tension between possibility and prohibition is a recurring theme in physics. Many phenomena are theoretically allowed, but practically unreachable. Wormholes may belong to this category, existing as silent features of cosmic architecture, inaccessible but influential. Still, the mere possibility reshapes our understanding. It forces us to reconsider the meaning of distance, the nature of space-time, and the limits of exploration. The universe may be far less isolated than it appears, stitched together by connections we are only beginning to imagine. As we move deeper into this exploration, we must confront an even more unsettling idea. Wormholes may not only connect distant places, but different realities, different universes, different versions of existence itself. The concept of wormholes becomes even more profound when extended beyond our own universe. Some theoretical frameworks suggest that wormholes could act as bridges between entirely separate universes, linking regions of a multiverse rather than distant points within a single cosmos. In these models, our universe is not alone. It is one bubble among many, each with its own physical constants, laws, and histories. Wormholes, in this context, are not shortcuts but interfaces, points of contact between fundamentally distinct realities. This idea arises naturally in certain interpretations of quantum gravity and string theory. Extra dimensions, compactified beyond direct observation, may provide the geometric space in which wormholes form. What appears impossible in 3 spatial dimensions may become natural in higher dimensional geometry. If wormholes connect universes, then black holes might serve as gateways not to destruction, but to elsewhere. Matter falling into a black hole in our universe could emerge through a white hole in another, preserving information while transforming its context. This would resolve long-standing paradoxes while opening entirely new questions. The philosophical implications are staggering. Our universe may not be a closed system. Events here could influence or be influenced by regions beyond our cosmic horizon. Reality itself becomes porous. Even within a single universe, wormholes challenge the notion of locality. Cause and effect may operate through pathways invisible to conventional observation. Correlations between distant events may not be coincidences, but consequences of hidden geometry. This reframing has implications far beyond astrophysics. It touches on the foundations of quantum mechanics, the nature of consciousness, and the limits of observation. If space-time is fundamentally connected in ways we cannot perceive directly, then our sensory experience captures only a fragment of reality's structure. Critics rightly caution against overreach. Wormholes remain hypothetical, and the mathematics that allows them does not guarantee their physical existence. Nature has a way of choosing the most conservative path, allowing equations to describe possibilities that reality never realizes. Yet history urges humility. Time and again, ideas once dismissed as absurd have proven essential. The expansion of the universe, the curvature of space-time, the existence of atoms, the reality of quantum entanglement. Each began as speculation before evidence forced acceptance. Wormholes occupy a similar position today. They sit at the edge of understanding, neither confirmed nor forbidden. Their study sharpens our theories and exposes their weaknesses. Even if wormholes never exist, the effort to understand them advances physics. There is also a psychological dimension to this fascination. Wormholes represent hope. Hope that the universe is not as isolating as it seems. Hope that exploration need not be limited by speed and distance. Hope that the cosmos contains pathways yet to be discovered, but there is also fear. Wormholes undermine certainty. They threaten causality, predictability, and control. A universe riddled with hidden tunnels is not easily mapped or mastered. It resists confinement to simple narratives. Perhaps this is why wormholes captivate us. They sit at the intersection of possibility and mystery. They promise access while withholding clarity. They invite exploration while warning of danger. As technology advances, we may one day probe space-time with sufficient precision to detect its hidden topology. We may map gravitational fields with exquisite detail, uncovering anomalies that hint at deeper connections. Or we may find nothing and conclude that wormholes belong only to mathematics. Either outcome reshapes our understanding. What matters is the question itself. Are we truly isolated islands in an expanding void, or participants in a vast interconnected structure whose pathways lie just beyond perception? The universe does not owe us simplicity. It has already shown that it is capable of astonishing complexity, subtlety, and surprise. Wormholes may be another expression of that truth. As we approach the end of this journey, one final perspective remains. Even if wormholes cannot be used, even if they exist only fleetingly or invisibly, they may still shape the universe in profound ways. They may influence how space-time evolves, how information flows, and how the cosmos organizes itself on the deepest level. They may be the scaffolding beneath reality, unseen but essential. And that possibility alone is enough to change how we look at the stars. When we gaze into the night sky, we see distance. Vast, cold, unforgiving distance. Light years stretch between stars. Galaxies drift apart, and the universe seems to expand endlessly, carrying everything away from everything else. This vision has shaped our sense of cosmic loneliness, but wormholes challenge that narrative. They suggest that the universe may be closer than it appears. That separation is not absolute. That beneath the apparent emptiness lies a hidden architecture of connection, subtle and profound. Whether wormholes exist as physical structures or remain theoretical constructs, they have already done something remarkable. They have forced us to rethink what space and time truly are. They have exposed the limits of intuition and the power of mathematics to reveal unseen possibilities. Wormholes remind us that reality is not obligated to conform to human expectations. The universe is under no requirement to be intuitive, comfortable, or simple. It is free to be strange, and perhaps that is the most important lesson. Science advances not only by answering questions, but by asking better ones. Wormholes represent a question so deep that it touches nearly every aspect of modern physics. Gravity, quantum mechanics, information, causality, and geometry all converge at their threshold. We may never travel through a wormhole. We may never even observe one directly. But the search itself expands our understanding. It pushes theory to its limits and invites new ways of thinking about existence. In that sense, wormholes are already doing their job. They are teaching us humility, teaching us that what we see is not all that exists, teaching us that the universe may be more connected, more intricate, and more mysterious than we ever imagined. If the cosmos does contain invisible highways, then we are only at the beginning of learning how to read the map. And if it does not, then the attempt to find them will still have revealed truths just as profound. Either way, the journey continues. If this exploration has expanded your perspective, challenged your assumptions, or sparked new questions, then take a moment to stay connected. Subscribe for more deep journeys into the mysteries of the universe and share your thoughts below. The conversation does not end here, because the greatest discoveries are often not answers, but invitations to look deeper. And the universe is still inviting us.